Hello dear students. In the previous video, I have discussed the ACES final examination chemistry question paper of 2024. In that video, I have discussed from question number 1 to 10. Now today, I will start from question number 11. In question number 11, it is asked, define conductivity and molar conductivity for the solution of an electrolyte. Discuss their variation and concentration. So this is the answer. Conductivity is the ease with which an electric current passes through an electrolyte solution. It can also be defined as the conductance of a solution that is 1 centimeter long and has a cross-sectional area of 1 centimeter square. Conductivity is the inverse of resistivity and its unit is Siemens per centimeter. Molar conductivity, which is denoted by lambda m, of a solution at a given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte kept between 2 electrodes with area of cross-section A and at a distance of unit length. Its unit is per ohm centimeter square per mole or Siemens centimeter square per mole. The conductivity of an electrolyte solution always decreases with decrease in concentration, that is, on dilution. This is because with dilution, the degree of dissociation increases and the total number of current-carrying ions increases, but the number of ions per unit volume decreases. The molar conductivity of strong and weak electrolytes increases with dilution, that is, decrease in the concentration. This is because with dilution, the degree of dissociation increases and the total number of current-carrying ions increases. Next, question number 12. So that the half-life period of a first-order reaction is independent of the initial concentration of the reactant solution. We know that for a first-order reaction, the rate equation is K is equal to 2.303 by T log concentration of R0 by concentration of R, where R0 is the initial concentration and R is the concentration at time T. K is the rate constant. At T is equal to T half is the half-life time, concentration of R becomes concentration of R0 by 2. You have to remember the half-life of a reaction. The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial concentration. So at T is equal to T half, R0 becomes R0 by 2. One implies put the value of T and concentration of R. Equation 1 becomes K is equal to 2.303 by T half log R0. Put the value of concentration of R, R0 by 2. You will get this one, 2.303 by K log 2. R0 cancel out. Then 2.303 by K into the value of log 2 is for 0.301. Then multiply with 2.303. You will get 0.693 by K, which is a constant. K is a constant, rate constant. This one is also a constant value. That's why whole value is a constant. That's why the half-life period of a first order reaction is independent of the initial concentration of the reactant. This is the answer. Next, another question is given as or in question number 12, which is the initial concentration of N2O5 in the following first order reaction. This is the reaction was 1.24 into 10 to the power minus 2 mole per liter at 318 K Kelvin. The concentration of N2O5 after 60 minutes was 0.20 into 10 to the power minus 2 mole per liter. Calculate the rate constant of the reaction at 318 K. Now, this is the answer. Here, the initial concentration is given as 1.24 into 10 to the power minus 2 mole per liter. And after 60 minutes, the concentration is given 0.20 into 10 to the power minus 2. This is the concentration of R, that is concentration of the reactant after time T. And time is 60 minutes. We know that for a first order reaction, rate constant K is equal to 2.303 by T log initial concentration divided by concentration at time t. Put the value of t 60 log concentration, put the value of concentration of initial concentration, which is this, and concentration at time t is this. It is given, and after final calculation you will get this value 3.04 into 10 to the power minus 2 per minute. Next, question number 13. A reaction is first order in A and a second order in B. Write a differential rate equation. How is the rate affected on increasing the concentration of B 3 times? See the solution. It is given that a reaction is first order in A and second order in B. In this case, the differential rate equation becomes rate is equal to K, concentration of A, concentration of B. Since the reaction is of first order in A, that's why the power of A will be 1, and second order in B, that's why the power of B should be 2. So this is the rate equation. Next, come into the second question, that is B. On increasing the concentration of B 3 times, the rate becomes 9 times. Why it becomes 9 times? As we know, rate of equation dr by dt is equal to Ka, concentration of B. Concentration of B becomes 3B whole square is equal to 3 square 9K AB square. 9 times increases. The rate of the reaction will increase 9 times. This is the answer. Question number 14. Calculate the magnetic moment of a divalent ion in aqueous solution if its atomic number is 25. Solution. The atomic number is given, which is 25. The metal is Mn, manganese, with valence shell electronic configuration of 3d5 4s2. You have to know the electronic configuration of that atom whose atomic number is 25. The outermost electronic configuration is this 3d5 4s2. The divalent ion Mn2 positive has valence shell electronic configuration 3d5 4s0. Mn2 positive, 2 electron loses from the 4s orbital. It contains 5 unpaired d electrons. That's why n value becomes 5. Its spin-only magnetic moment is root over n into n plus 2. This is the formula of spin-only magnetic moment. Put the value of n, 5 into 5 plus 2, it becomes root over 35, which is equal to 5.92 bm. Bm indicates Bohr magneton. Next, question number 14. It is given as OR. What are transition elements? Give the general electronic configuration of transition elements. According to IUPAC defines transition elements as an element having a d subshell that is partially filled with electrons, or an element that has the ability to form stable cations with an incompletely filled d orbital. The general electronic configuration of transition elements is n-1 d 1 to 10 ns 1 to 2. This is the general electronic configuration, and d orbital from 1 to 10 electrons may be present. In s orbital, 1 to 2 electrons may present. Next, come into the question number 15. After having completely filled d orbitals 4d10 configuration in silver atom in its ground state, how can you say that silver is a transition element? This is the answer. Silver is a transition element because it has incomplete d subshell in its most stable oxidation state. Silver, as it has a completely filled 4d orbital, 4d10 5s1 in its ground state, but as it shows two oxidation states, +1 and +2. In the +1 oxidation state, an electron is removed from the s orbital. However, in the +2 oxidation state, the electron is removed from the d orbital. Thus, d orbital now becomes incomplete, which is a 4d9 configuration. Hence, it is a transition element. This is the main reason. Another question is given as OR in question number 15. which is Zn2 positive salts are colorless, while Cu2 positive salts are colored. Give reasons. Answer is Zn2 positive has 3d10 configuration and no unpaired electrons. Hence, it is colorless. Whereas in Cu2 positive state, which is 3d9 configuration, there is one unpaired electron and it undergoes DD transition, emitting color. So Cu2 positive salts are blue in color.